Hello everyone. In this presentation, I will evaluate the spatial variability of heavy metal transport in unsaturated soil, which uses scale factors to quantify the variable sorption isotherms. When the heavy metal with the rainfall goes into the soil, it will be regarded in soil and continue transported downwards. A lot of studies have been reported its contribution about the heavy metal transport in soil. And many attentions have been focused on the heavy metal transport process in the soil plume at 1D. How to extend this sorption process into 2D or 3D is still an open question, because the soil is heterogeneous, which makes the transport process highly variable. Usually when we describe the soil properties at the field scale, we use an average value from all of the sampling points to describe the soil properties. But as you can see, the transport behavior is not described with a single value, but functional dependencies, which makes the upscaling from the point measurement to large scale problematic. So, since the sorption can represent the retardation of heavy metal in soil, so the quantification of sorption process could be provide a pathway which could be used to quantify the spatial and temporal heavy metal transport in 2D or 3D. We use a recent developed method, a calculation of scale factor, to quantify the spatial variability of heavy metal sorption in soil at the field scale. Actually, the scaling is used as a hydrology area to quantify the variation of water retention curve. In 1956, Miller and Miller proposed a great concept that in pore system, for water flow in soil, the pore system in water for water flow in soil are similar, so the water retention curve could be scaled. In 1984, T. Lawson and Nielsen point out that the scaling is in principle actually also applicable to the other valuable soil properties. So in 1997, Böttcher has developed a theory. The scale factors alpha are based on the assumption that between different systems, there's always a geometrically interpretable similarity, just like these figures, which differ only by different characteristic lengths. Their characteristic properties can be transformed from one into another. If our soil particle system also has this geometrically interpretable similarity or the sorption similarity, then the concentration of solution around the particle can be converted with scale factors in each other. The scaling needs a rule. According to the time, I don't want to explain every details of these equations, but two parameters are needed to be known: the main concentration to derive reference isotherm and the scale factors are. More details are given in the Böttcher 1997. So, the heavy metal sorption behavior can be described with the sorption isotherm. When we put all of the sorption isotherm in one diagram, they varies very much, just like in this figure. And so after scaling, the wide spread of sorption isotherm is reserved into an average relation. This curve, we call it the reference isotherm, and the variation is through scale factors reserved. A major aim to calculate the scale factor is to make the sum of deviations square between after-scaled isotherm and the reference isotherm and smallest, which is expressed by the scaling efficiency. Furthermore, the scale factor were found in Böttcher's study that they are correlated with some soil physical-chemical properties. That means it can be derived from the after-scaled the scale factors from soil physical-chemical properties. And let's think about this situation. If our soil, if we put all of the soil sample from the study area with equal amount, based on the assumption of sorption similarity, that means we mix the average first on the mixed soil sample. If the measured sorption isotherm is comparable with the after-scaled average isotherm, that means it can be used to be the reference sorption isotherm. So the function of scale factors is no more limited as the describing of spatial variability, and now can be extended to predict the sorption behavior in soil. We propose two different scaling procedures. First one is the direct scaling procedure with calculating mean sorption isotherm and scale factors. The second one is the indirect scaling procedure with sorption isotherm, which derive from mixed soil sample and the scale factors, which are transformed from soil properties using linear regression. A little information about the water flow and heavy metal transport. The major matter of heavy metal goes into the soil in the nature is the atmospheric deposition. So the water balance at the upper boundary is Q equals P minus AT, where Q is the water flux density, P is the precipitation, and AT is the evapotranspiration. In the unsaturated soil, the water flow is usually vertical, so the simultaneous heavy metal transport is also vertical and can be derived from this this equation, this convection dispersion equation. This equation has two dependent variables, C and S. S could be eliminated using the sorption isotherm. So one variable C is now left, which is our input concentration into the soil. In 2010, we have investigated the spatial variability of heavy metal sorption in Latvia, southwest of Hanover. It's the piece of farmland. The soil is made from alluvial soil and developed in loess material. In order to distinguish the impact of different soil horizons to the sorption behavior, we took samples from two soil horizons, from 0 to 30 centimeter topsoil and 13 to 16 centimeter subsoil. For each horizon, 15 samples were taken from 250 meter transect at every 5 meter intervals. And also you can see the position which is marked as the red line in the map. So the soil properties were measured in the lab: pH, texture, effective equation exchange capacity, organic carbon content, oxalate, extractable oxides. All of these are reported to be relevant to the sorption behavior. And the sorption isotherm is also measured in the lab, and cadmium, zinc, copper were chosen, and their sorption isotherm were fitted to the Freundlich isotherm, which has two parameters, K and N. So in this table, two statistical characteristics for the soil properties and Freundlich parameters are listed here, the mean and the coefficient of variation. Due to the high pH, the sorption behavior are also high. And for the quantification of variability, the coefficient of variation very important. as you can see, the soil properties vary not so much except the CEC. And for the sorption isotherm, K varies much bigger than N. So for the direct scaling procedure, I put some examples here. These are the sorption isotherm. These three are the before scaling, and these three are after scaling. So as you can see, the variable sorption isotherm after scaling is, are reduced, and the sum of deviation square before and after show us also a big difference. For the indirect scaling procedure, the scale factor alpha can be calculated, as I just said, using the linear regression from the soil properties. The contribution of different soil properties are listed here. What I want to say is the sorption is a complex process. Different heavy metal really want to different soil properties. As you can see, pH is important for cadmium and zinc sorption, and in contrast, the CEC is more important as than pH to copper. Another valuable parameter is this adjustable coefficient of determination, which shows us only a moderate significance and makes us worry about the result of indirect scaling procedure. In this table, all information about the reference isotherm and scale factors are listed. Good news is that the reference isotherm between different scaling procedure fit each other quite well, and the scaling efficiency are almost high. Bad news is that the coefficient of variation for the indirect scale factors are smaller than the direct scale factors, reflected to the sorption isotherm, the variability could be reduced. So, in Hydrus, we set this geometry as a rectangle which has a longitudinal 250 millimeter and vertical long 0.6 meter. It is divided into 15 soil plumes for each soil horizon, and each one has a single set of K and N, certainly also the scale factor alpha. The infiltration rate was set at about 250 millimeter per year, and the input concentration for different heavy metal and the simulation term are listed here. So, three scenarios will be simulated. Scenario 1 will be simulated with the original sorption isotherm. After I show you all of these scenarios, a comparison will be made. So let's go to the scenario 2. In scenario 2, the input data was no longer the K and N of sorption isotherm, but now is the reference isotherm and scale factor from direct scaling procedure. And in scenario 3, the input data were changed with the sorption isotherm from the mixed soil sample and the scale factors from the soil properties. So now the comparison. Firstly, a common phenomenon can be observed between different scenarios for all of these three heavy metals. That is the variability of transport of scenario 1 is bigger than scenario 2 and bigger than scenario 3. And between different heavy metals, the zinc after scaling show almost perfect matching to the original transport compared to the cadmium and copper, which could be relevant to the scaling efficiency, which 88% of zinc is bigger than cadmium and copper. And also could be relevant to the coefficient of variation of K and N is close to the coefficient of variation of scale factors. So, respecting to the great number of sampling, no soil plume simulation experiment was made to compare with this simulation, but we still can learn something from this simulation. Although the transect is only 250 meters, the heavy metal transport is obviously variable. And so it's worth it to investigate the spatial variability of heavy metal transport. We conclude that the scale factor for the direct scaling procedure can describe the spatial variability of heavy metal transport well only when the sorption isotherms themselves is not so variable, such as tin. And for the some variable conditions such as cadmium and copper, the scale factors are not so effective. And for the indirect scaling procedure, the prediction accuracy must be improved. Thanks for your attention.